So this is a problem session which is based on the material that was covered in week 10 of this course. Let's begin by considering a problem where we deal with the matrix of a given linear operator with respect to an orthonormal basis. So that's the problem 1. Let T from R3 to itself be a linear operator which has an upper triangular matrix with respect to a given basis, to the basis, let's call it beta, which is given by 1 0 0 1 1 1 and 1 1 2. So we know that T has an upper triangular matrix with respect to this basis. The problem is to find an orthonormal basis of R3 with respect to which T has an upper triangular matrix. Can immediately check that the given basis is not orthonormal. In fact, it's not orthogonal at all. So the question is to get hold of a basis which is orthonormal and with respect to which the matrix of T is upper triangular. Okay, so before we even start solving for this problem, let's revisit the process of Gram-Schmidt orthonormalization. So I'll first solve the problem in a more general setting and then eventually compute the orthonormal basis that is given here. So more generally, so let's come back to the problem a few minutes later. Let's look at a digression. So let V be a finite dimensional inner product space. And let's start off with some basis, say V1 to Vn, such that given T in say L of V, the matrix of T with respect to beta is upper triangular. What does it mean for the matrix of T to be upper triangular? This means that TVK is in the span of V1 to Vk. If you carefully go back and check what the meaning of upper triangular is, it means that if you look at TVK and the column representation of it, it will have only diagonal above the entries above the diagonal to be zero, to be non-zero. All the entries below the diagonal will be zero. That means that the coefficients of the terms V1, V2 up to Vk contribute in the expansion of tvk in terms of v1 to vn, and the coefficients of vk plus 1 to vn do not contribute. So therefore tvk belongs to span of v1 v2 up to vk. Now let's apply Gram-Schmidt orthonormalization to the basis beta. So let's, did I give a name? Yeah, to beta, and obtain say beta prime, which is equal to say w1 to wk. So wk or wn to begin with, it was wn. So let me be careful here. Yeah. So beta prime is obtained by Gram-Schmidt orthonormalization of v1, v2 up to vn. And therefore, we get hold of vectors w1, w2 up to wn. But the Gram-Schmidt orthonormalization was not just giving us orthonormal vectors, it was also at every stage ensuring that span of W1 to Wk is also equal to the span of V1 to Vk. This is true for all 1 less than or k less than or equal to n. This is the case that the process of Gram-Schmidt orthonormalization ensured this particular property. So if you look at T, let's look at T Wk now. Now notice that Wk in particular, we are interested in TWk for L up to from 1 to n, so that we can compute the matrix of T with respect to beta prime. So what do we know about TWk? What do we know about Wk? We know that Wk in particular belongs to the span of V1 to Vk, and therefore Wk is just A1 V1 plus something up to say AK Vk. And if you look at TWk, this is just going to be equal to A1 TV1 plus up to AK TVK. But each of these TVIs, TVJ, this belongs to span of V1 to Vj for all, each of the j, right? For all 1 less than or equal to j less than or equal to k. This would imply that TWk, this term belongs to in particular span of W1 V1 V2 up to Vj. This is contained in the span of W1. So let me write it like this. This is contained in the span of V1 to Vk, which is equal to the span of W1 to Wk. So what do we have? We have each of the TVj belongs to the span of W1 to Wk for all 1 less than or equal to j less than or equal to k. Why is this the case? This belongs to this particular relation comes up because of the fact that the matrix of T with respect to beta is an upper triangular matrix. This comes up because the span of V1 to Vk will in particular contain the span of any subset of V1 to Vk, and the final one is because of Gram-Schmidt orthonormalization, which implies that each of the TVj belongs to span of V1 V2 up to Vk, and hence TWk, which is A1 TV1 plus up to AK TVk, also belongs to the span of V1 W1 to Wk. But what does this imply? This implies that the matrix of T with respect to beta prime is upper triangular. This is precisely what it means. So if we start off with a basis with respect to which our given linear operator is upper triangular, and if we do a Gram-Schmidt orthonormalization of that particular operator, we get a new basis. Again, that will be an orthonormal basis with respect to which our linear operator continues to be an upper triangular matrix. So now let's get back to our problem. Our problem was to find an orthonormal basis of R3 with respect to which T has an upper triangular matrix, given the condition that T is already upper triangular with respect to our basis 1 0 0 1 1 1 and 1 1 2. Okay, so let's now solve for our given problem. Solution to problem 1. Getting back from the digression. So recall that our T belonged to L of R3 upper triangular with respect to beta, which was 1 0 0 1 1 1 and 1 2 3. I guess let's go back and check 1 1 2 1 1 1 0 0 1 1 1 and 1 1 2 1 0 0 1 1 1 and 1 1 2. So the only thing that we have to do is to apply Gram-Schmidt orthonormalization to beta with respect to the standard inner product. Of course, the inner product, because it was not mentioned, we will assume that the inner product involved is the standard inner product. So with respect to the standard inner product, let's orthonormalize our given basis here. So this is say V1, V2 and V3. So W1 prime will be equal to V1 itself. What will be W2? W2 will be W2 prime. Let's calculate W2 prime. That's going to be 1, 1, 1, which is V2 minus the inner product of V2 with W1 prime by the length of W1 prime square, which is 1 times W1 prime. And this is just 1, 1, 1 minus 1, 0, 0, which is equal to 0, 1, 1. That's W2 prime. And what about W3 prime? W3 prime will just be equal to 1, 1, 2 minus the inner product of 1, 1, 2 with 1, 0, 0 times 1, 0, 0 minus the inner product of 1, 1, 2 with 0, 1, 1 by the length of W2 prime square, which is 2 times 0, 1, 1. So this is just 1, 1, 2 minus, this is just 1 times 1, 0, 0 again. So this is 1, 0, 0 minus 1 plus 2 is 3 by 2, 0, 1, 1. Let me be careful. 1 plus 2 is 3. Yeah, 3 by 2. Alright, so this is just going to be equal to 1 minus 1 is 0, 1 comma 2, 0 comma 1 comma 2 minus 0, 3 by 2, 3 by 2, which is equal to 0. 1 minus 3 by 2 is minus of half. 2 minus 3 by 2 is half. And therefore, W2 prime is obtained in this manner. So what will be our orthonormal basis? So W1 will be, after normalizing, it's just going to be 1, 0, 0. W2 prime will be 0, 1, 1, and after normalizing, it will be 1 by root 2 times 0, 1, 1. This is W2. W2 is W2 prime by the length of W2 prime. And how about W3? W3 will be again W3 prime by, so this is half of 0 minus 1, 1. This will be 1 by root 2 times 0 minus 1, 1. So this is the orthonormal basis that we obtained by Gram-Schmidt orthonormalization of our given basis. And because T was upper triangular with respect to beta, so T will be upper triangular with respect to beta prime, the orthonormal basis, which is given by W1, W2 and W3. So I don't even have to sit and compute what the matrix of T will be. Of course, we can't do that because we don't know what T is, but nevertheless, from the theory that we have developed and from the abstract mathematics that we have already seen, we can conclude here that T will be upper triangular with respect to this orthonormal basis. Okay, so that's more or less the first problem. I would like to give you an exercise here at this point of time, which was already in some sense covered in the digression that we did just a few minutes back. Check that. Okay, it will be what is. So let's get back to the setup of let V be an inner product, finite dimensional inner product space. And let beta prime be obtained by the Gram-Schmidt orthonormalization of basis beta. Then what will the matrix change of basis matrix from beta to beta prime look like? Then what will be what can we say about what will be, will not be? We cannot compute it explicitly because we don't know what beta and beta prime is. It will depend on beta and beta prime, but what can we say about the change of basis matrix from beta to beta prime? Well, the digression should tell you that this is going to be an upper triangular matrix. So the next problem deals with computing an orthonormal basis of the orthogonal complement of a given subspace. So let W be equal to the span of 1 0 I and 1 2 1 in C3. Then compute an orthonormal basis of the orthogonal complement of W. So at this point I would like to remind you that if let me call it solution. So let's do one thing. Let's extend beta. Let's extend 1 0 I and 1 2 1. Notice that that is linearly independent, and if you add one more linearly independent vector, we will get hold of a basis of C3. So let beta be say 1 0 I 1 2 1 and let's say 0 0 1 be a basis. So the first thing to check is whether it is a basis obtained by extending the basis of W. So that is what we have done. And suppose we have, let's call it V1, V2 and V3, and we orthonormalize this particular basis beta to obtain beta prime. So let beta prime equal to W1, W2 and W3 be obtained by the Gram-Schmidt orthonormalization. Then what do we know? We know that span of V1, V2 is the span of W1, W2, and therefore that will be a basis of W, and W3 will be a basis of the orthogonal complement of W. Notice that dimension of orthogonal complement is going to be equal to the dimension of C3 minus dimension of W, right? So then, so let me just complete whatever I was writing. Then W3 will be a basis of orthogonal complement of W. So notice that the dimension of the orthogonal complement of W, this is equal to dimension of C3 minus dimension of W, which is equal to 3 minus 2, which is equal to 1. So it's correct. Everything is falling in place. W3 will be one vector which will form a basis of W, orthogonal complement of W. All right. So let's compute the vector W in here. But before that, I would leave it as an exercise for you to check that so there is one thing which you will have to check. The vector V3 is not linearly dependent on V1 and V2. That I will leave as an exercise for you. And let's jump to computing the vector W3, which is obtained by orthonormalization of beta. So recall what beta was. Beta was 1 0 I 1 2 1 and let's take the next one to be 0, 0, 1. So this is our beta, the ordered set consisting of these three vectors. Okay, so what will be w1 prime? W1 prime will be just 1, 0, I. W2 prime will be equal to 1 to 1 minus the inner product of 1 to 1 and 1, 0, I divided by 2 times 1, 0, I. The quick computation should tell us that this is minus of 1 minus of I by 2 times 1, 0, I. Notice that this is an inner product in C3, so the complex conjugate will come in from the second vector, and therefore minus I will come in here. 1 minus I is right, so this is correct. So this is just going to be equal to 1 minus 1 minus I, which is 1 plus I by 2, and then 2 here. And how about the last one? 1 minus I by 2 times I. So this is just going to be equal to 2 minus 1 minus 1, which is going to be 1 minus I by 2. Should check that this is indeed correct. And what about W3 prime? W3 prime is what we are interested in. W3 prime will just be equal to 0, 0, 1 minus the inner product of 0, 0, 1 with 1, 0, I by 2 times 1, 0, I. The 2 below is basically the length of W1 prime square, and there will be one more term. This is just going to be the inner product of 0, 0, 1 with our W2 prime, which is, okay, so let's just do one thing. This is just half 1 plus I 4 1 minus I. So this is going to be 1 plus I 4 1 minus I by, what is the length of this square rather. This is going to be 1 plus 1 2. Maybe I should just compute the length of this here. Length of this is just going to be 1 by 4 plus 1 by 4 is 1 by 2 plus 4 plus 1 by 2, which is equal to 5. So this is just 5 times 1 plus I by 2 to 1 minus I by 2. Okay, let's compute what this vector is. It's quite computational, as I was indicating a bit earlier. This is going to be 0, 0, 1 minus the term here will be contributing will be minus I. So minus will be I by 2 times 1, 0, I minus, I hope I'm not making a mistake. This is going to be 1 plus I. Oh, there is a into 2 that will come in here because there's a half which I missed. So this is half, and yeah, this is right. So this is going to be 1 plus I by 10 times 1 plus I by 2, 2, and 1 minus I by 2. Okay, so this is, maybe there is some mistake. Yeah, we'll see what the mistake is, if at all there is one. I by 2 times 1, 0, I minus 1 plus I the whole square is I by 10, and well, I plus 1 by 5, and 1 minus I square is basically 2, and this is just going to be 1 by 10. Okay, let's compute further. This is going to be I by 2 minus I by 10, which is going to be equal to 5 minus 1, 4I, so 2I by 5. And the next one will just be equal to minus of I plus 1 by 5, and this is minus of 1 by 2 minus 1 by 10. Or did I miss a sign here somewhere? I minus 1 minus I square, 1 plus 1, that is 2 by 10, that is right. This is all right. So this is just going to be minus of 2 by 10, which is going to be 1 by 5. Yeah, I made a mistake. This is not going to be, yeah, this is 2. This will be minus of 1 by 2. This is also going to be 2 by 5. And therefore, so if you are to extract things out, this is just going to be equal to 2 by 5 times I minus of 1 plus I by 2 and minus of 1. And you orthonormalize it by, so you can forget about this. Let's see, what is this? This is just going to be equal to square root of 1 plus, this is half plus 1 by 4 plus 1 by 4 is half plus 1, which incidentally turns out to be root 2 by to the power 1 by 2, root 2 by root 5 times I minus of 1 plus I by 2 and minus 1. So this is the orthonormal basis of our given vector. So I should have just left these calculations to you, but once in a while it's good to do the calculations in front and see how it's coming out. All right, so that is the basis of the orthogonal complement of our W. All right, so I made a mistake here. So let me just do a minor correction. This is just going to be equal to I by 2 0 and minus 1 by 2 1 by 2. So this is going to be 1 by 2 here minus the same quantity. So this is just going to be equal to I by 2, and hence here it will just be equal to minus of I. Minus of I square will be minus 1 times minus 1, and hence this will be equal to 1 by 2, which makes sense. So here this will just be equal to half minus 10, 1 by 10, which is 5 minus 4. So this is going to be plus 2 by 5. So this is going to be plus, but this doesn't change, and therefore this is going to be plus. So I think I was making a minor mistake. Yeah, I've rectified it. So the next problem deals with finding the distance of a given vector from a given subspace in R3. So let me write it down. Problem 3. So in R3, compute the distance of the vector, say u is equal to 2 1 3 from the subspace W, which is equal to the set of all x y z, such that x plus 3y minus 2z is equal to 0. So yet again, this is going to be a computational problem. What the problem demands is to find the distance of the vector 2 1 3 from W. So how do we go about solving such a problem? So there are certain theorems which we have already done, which captured the particular vector in our given subspace which is nearest to the given vector, which we had called the projection of 2 1 3 onto W. So if you recall, what we had done was that we computed the orthonormal basis of W, looked at the projection as being the unique vector, such that, let's call the unique vector V, such that there is a unique W, such that our given vector can be written as V plus W. And this vector V is the closest vector in W to our given U. We just have to compute the length of U minus V. So I'll write it down explicitly and describe what I just said. So what we will do is let beta be equal to, let's pick two vectors from W which are linearly independent and which will turn out to be a basis. Let beta be equal to say minus 3 1 0 and say 2 0 1 be a basis. Yeah, you should check that this is a basis of W, and let's orthonormalize this particular basis to beta prime. Let beta prime be equal to W1 W2 we obtained by orthonormalizing it. We obtained by the Gram-Schmidt orthonormalization. Let me just write it in short here. So what will our W2 be? It is just going to be equal to 201 minus the inner product of 201 and minus 310 by the length of W1 square, which is 10 times minus 310. Okay, so this is equal to 201 minus, let's see, this is minus 6 by 10, which is minus 6 will be plus now 3 by 5 times minus 310. Minus 3 into 2 is 6. The other terms don't contribute, so minus 6 by 10 is minus 3 by 5, minus and minus will be plus. Yes, this is right. So this is equal to minus of 9, so this is 1 by 5, 3 by 5 and 1. So this is obtained by orthogonalizing W2. And now let's see what is the projection of 213. Then the projection of 213, which will give you the vector which is closest to 213, this vector 213. This the closest vector in W to 213. The projection will be, if you recall, that is given by let U is already taken, V be equal to the inner product of 213 with say W1 times W1 plus the inner product of 213 with W2 comma W2, where W1 and W2 are obtained by, oh, this is actually prime. You have to orthonormalize it, make it norm 1, and that is how you will be getting hold of the projection. You should go back to your lectures and check. That is precisely what we had done. So here the first vector is minus 3 1 0, so this is going to be minus 3 1 0, inner product of 2 1 3 with this into minus 3 1 0. The normalization has to take place. Let me write it here, 1 by 10 plus 2 1 3, and what was the new vector that we got? 1 by 5, 3 by 5 and 1. So let me just write it as 135, 135, now product of this with the given number by 25 plus 9, 34, 35. This is precisely the projection onto our subspace W. So let's just compute this very quickly. Okay, so this is just going to be minus 6 plus 1 minus 5. So this is minus of 1 by 2 times minus 3 1 0 plus 2 plus 3 5 plus 15 is 20. So 4 by 7 times 1 3 5. And if we compute this, this is 3 by 2 plus 4 by 7. So 21 plus 8, 29 by 7. 4 by 7 minus 1 by 2. So I'll just write it down. Maybe one more step won't hurt. So this is 3 by 2 plus 4 by 7. 12 by 7 minus 1 by 2. And 5 4s are 20 by 7. This is our projection onto our subspace W. So let's see what this is. This is 29 by 14. This is 24 minus 7 is 17 by 14, and this is 20 by 7. So this is the vector in W which is closest to 2, 1, 3, and then what is going to be the distance of our vector to the subspace? It's just going to be the distance of our vector to this particular vector, and hence distance of 2, 1, 3 to W is given by, so this distance is with respect to the length that we are obtaining from our given inner product. So this is going to be the length of 2, 1, 3 minus 29 by 14, 17 by 14 and 20 by 7. This is going to be equal to minus of 1 by 14, 14 minus 7 is 14 minus 17 is minus of 3 by 14, and 7 3s are 21, 1 by 7. The length of this, which is going to be equal to 1 by 14, the square root of 1 by 14 square into 1 plus 9 plus 4, which is equal to 1 by square root of 14. So this is precisely the length of our given vector to our given subspace. So the next problem that we will be solving is what is popularly known as Bessel's inequality. Let's look at the problem. So assume that V1 to Vk is an orthonormal set. In an inner product space V. Let U be some arbitrary vector in capital U. Then prove that the inner product of U with Vj square, where the summation is from 1 to k, this is less than or equal to the length of U square. Note, observe that this is a inner product space, and this inequality is always satisfied for any collection of orthonormal vectors. With equality, there is we know exactly when the equality happens. With equality, if and only if U belongs to the span of V1 to Vk. Okay, so let's do one thing. Let's give a proof of this. So let U be equal, or rather V be equal to the vector given by inner product of U with V1 times V1 plus up to U with Vk times Vk. Now if you observe that U minus V, if you look at the inner product of this with say Vj, this is just going to be equal to U with Vj minus the inner product of V with Vj, which I will just directly write it as U with Vj, which is equal to 0. So this implies that U minus V is orthogonal to Vj for all j from 1 to k. That means if W is equal to the span of V1 to Vk, then U minus V is orthogonal to W. In particular, So let me call u minus v as something. Let w be, so let w be equal to u minus v. Then inner product of w with vj is going to be this. So in particular, w is also orthogonal to our given v. So what do we have? We have hence u is equal to v plus w, where v is orthogonal to our w. So what can we say about the length of u square? Length of u square, now by the Pythagoras theorem, if you go back and check, there was no assumption of any finite dimensionality to talk about Pythagoras theorem. This is just going to be equal to the length of v square plus the length of w square. And that would imply that the length of u square is greater than or equal to the length of v square, or length of u is greater than or equal to the length of v. No, this is precisely what we had set out to prove, right? What was length of v square? V was this. So length of v is just going to be the sum of absolute value of the inner product square. Yeah, so recall that v was just inner product of u with v1 times v1 plus up to the inner product of u with vk times vk, and therefore the length of v square is just equal to summation of the absolute value of u with vj square, where j is from 1 to k, and that establishes Bessel's inequality. When can we say about equality? We can say that the equality happens if this w is 0, right? With equality, if and only if w is equal to 0. But what does that mean? That means that this is if and only if u is equal to v, which is if and only if u belongs to w. Alright, so we had set out to prove this inequality, and the equality is something which we just observe as following when w is equal to 0. And with that, we have completed the proof of Bessel's inequality. Alright, so let me stop here.